So, um, imagine this scenario. You've been working on a housing price prediction model for weeks. You've tuned the neural network architecture. You've, meticulously cleaned the data, handling every missing value and outlier.
You're feeling pretty good about it at this point.
Exactly. You hit that sweet spot. 84% validation accuracy. You're ready to deploy this to production. But then you decide to make one tiny, seemingly harmless tweak to how you pre-process the data.
Oh, I know exactly where this is going.
Right. You don't touch the layers. You don't change the learning rate. You just adjust a scalar to normalize the inputs. You run the validation again, and suddenly, 61%.
Yeah, that is the exact moment your stomach just drops through the floor. It's not just a bad result, it's an absolute catastrophe.
It's a total disaster. 84 to 61 in the blink of an eye. You scramble. You check the code diffs. But the model architecture is identical. The data source is the same. You start doubting your own sanity.
Because it doesn't make any logical sense on the surface.
Right. And the reveal, when you finally find it at 2 a.m. after drinking like 4 coffees, is that the root cause was a silent mutation.
Ah, yes. The silent mutation. The silent killer of ML pipelines everywhere.
Exactly. Feature scaling modified the data set in place because, completely unbeknownst to you, your training set and your validation set were actually pointing to the exact same memory object.
Which means you didn't train a model and test it on new data.
No.
You trained a model, corrupted the data it was training on, and then tested it on that same corrupted data. Your evaluation metrics are completely fraudulent.
You aren't testing generalizability at all. You're just testing how well your model learned the specific noise you accidentally injected.
It's brutal.
But wait, it actually gets worse. Let's talk about nightmare number 2. You were running 2 experiments simultaneously, right? Experiment A and experiment B.
Yeah.
You want to be efficient, so you write a script to loop through configurations.
Makes sense. Save some time.
Yeah. So experiment B decides to modify a configuration list, maybe adding a few extra hidden layers to see if it helps. You run the code, but somehow, inexplicably, experiment A's configuration changes too.
The spooky action at a distance bug.
Yes. You didn't touch experiment A, but because of a nested mutable structure trap, specifically a shallow copy, they were basically fighting over the same internal list in memory.
Experiment A was doomed before it even started because Experiment B hijacked its settings.
Exactly.
That is a classic, and it's so insidious because if you look at the code, it looks logically correct. You literally say to yourself, I made a copy of the config.
Yeah.
But you didn't understand what you actually copied.
And finally, let's hit the third scenario. You build a machine learning pipeline. It works. You run it again. It gives you a different result. You run it a third time. Different result again.
Inconsistency is the absolute enemy of engineering. I mean, if I can't reproduce your error, I can't fix it.
You just tear your hair out.
Yeah.
And the culprit, a custom transformer that corrupted the input array inside the transform method during cross-validation.
So the second fold of your cross-validation was training on data that had already been chewed up by the first fold.
Exactly.
These scenarios, I mean, they make my palms sweat just listening to them. And the most important thing for you to realize here is that none of these are syntax errors.
Right. The code runs.
Exactly. If you ran these through a linter or just tried to compile the code, Python would say, this looks great. These aren't beginner typos where you forgot a colon. These are memory model failures.
They are.
These are the silent bugs that cost companies millions in wasted compute and delayed launches.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here, we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
It is great to be here. And today, we are setting the stage for everything that follows in our curriculum. Today isn't just about Python syntax or learning how to write a simple loop. We are talking about the physics of ML data.
The physics. I mean, that sounds a bit intense for a coding deep dive.
Well, think about it. In the physical world, if I hand you an apple, I don't have the apple anymore. You have it. But in the digital world of memory, things are counterintuitive.
They really are.
Our goal today is to build a mental model of how Python handles memory so that you can write code that doesn't self-destruct, like those scenarios we just described.
And this is actually the foundation for week 1 of our curriculum, Python memory model and object references. But before we get into the real nitty-gritty, I have to ask, is this really necessary?
How do you mean?
Like, can I just rely on high-level libraries like PyTorch or TensorFlow to handle the memory for me? Why do I need to know what's happening under the hood?
That is a very fair question, and it's honestly one I hear a lot from junior engineers. They say, why do I care about memory allocation? I have 32 gigabytes of RAM.
Right. Memory is cheap now.
It is, but the answer is that those high-level libraries are leaky abstractions. They are built directly on top of Python's memory model.
So the foundation still matters.
Absolutely. If you don't understand how Python handles references, you will inevitably pass a 10 gigabyte tensor to a function, accidentally copy it, and crash your server.
Ouch.
Or even worse, you won't crash the server, but you'll modify the weights of a pre-trained model when you didn't mean to, and you won't realize it until your accuracy tanks in production.
Okay, so ignorance is not bliss here.
Yeah.
Ignorance is just a delayed outage.
Well said.
So let's unpack this. We need to start with the absolute core concept.
We do. And to do that, we actually have to unlearn something first.
Unlearn what?
The box analogy.
Oh, right. I think most people, when they start coding, especially if they come from languages like C or even just high school algebra, they imagine a variable is like a cardboard box.
Right.
If I write A equals 10, I have a box labeled A, and I literally put the number 10 inside it.
Precisely. And in some low-level languages or strictly stack-based scenarios, that's not a terrible way to think about it.
But in Python,
that mental model will lead you directly into the traps we discussed in the intro. In Python, variables are not boxes, they are references.
references,
Or, to put it simply, they are tags.
tags, like a name tag.
Exactly. Think of a Post-it note or a luggage tag. When you create an object in Python, like a massive data set or just the number 10, that object lives somewhere in memory. It has a specific address.
Okay.
The variable name A data model is just a Post-it note with a string on it tied to that object.
Okay. Let's visualize this for the listener. If I say A equals 1, 2, 3 in a list, I create a list object 1, 2, 3 somewhere in the memory universe. And I stick a Post-it note label A onto it.
Correct. The list exists independently of the name. The name is just how you find it.
Right.
Now here is where it gets really interesting. What happens when you write B equals A?
Well, if I'm thinking like a box person, I might think I copied the contents of box A into a new box B, like I photocopied the list.
Right, and that is the fatal flaw in the box mental model. You didn't photocopy anything.
I didn't.
No. In Python, assignment the equals sign never copies data. It only copies references.
Okay.
When you say B equals A, you are writing a second Post-it note labeled B and sticking it onto the exact same object.
Two names, one object.
Two names, one object.
Wait, hang on.
Oh.
If that's true, isn't that incredibly risky? It feels like I have two people trying to drive the same car at the same time. Why would Python be designed this way? It seems like it's asking for trouble.
It is risky if you don't understand it. But consider the alternative. Let's connect this to the bigger picture of machine learning.
Okay, let's do that.
Imagine you have a NumPy array that is 10 gigabytes in size. This is super common in deep learning or computer vision.
Sure, massive image data sets.
Exactly. If you pass that array to a function, say, process data, my huge array, and Python acted like a box language, it would have to copy all 10 gigabytes of data into a new box for the function to use.
Which would take time, a lot of time.
It would take massive amounts of time to read and write that memory, and it would blow up your RAM.
You'd run out of memory instantly. Your computer would crash.
Exactly. Instead, Python just passes the reference. It passes the address. It hands the function a Post-it note that points to the original 10 gigabyte array.
So it's instantaneous.
Instantaneous, zero memory cost for the transfer.
Okay, so that's the efficiency side of the sword. It's basically passing a pointer, for those who know C.
It is exactly passing a pointer. A variable in Python is essentially a PyObject pointer in C. It points to a struct in memory.
But here comes the other edge of that sword. If that function uses that Post-it note to find the array and then changes something in the array,
then everyone holding a reference to that array sees the change, because there is only one array.
wow.
If the function paints the array blue when the function returns, you are holding a blue array, even if you didn't want a blue array.
That is the fundamental trade-off.
Mm-hmm.
Speed versus safety. And understanding this references as tags model is the only way to navigate it.
Precisely. And to really understand the mechanics, we need to look under the hood of Python itself.
Let's do it.
Specifically, CPython, which is the standard implementation most people use. We need to talk about the life cycle of an object.
So how does CPython keep track of all these Post-it notes? Does it have like a master ledger?
It uses a system called reference counting. It's surprisingly simple but really powerful. Every single object in Python memory, whether it's a number, a string, or a massive tensor, carries a header structure with it.
What's in the header?
That header contains three things. It's type, so what is it? It's value, what data does it hold, and a reference count.
A counter, like a tally mark.
Exactly. Let's walk through the life cycle. You write equals 1, 2, 3. Python creates the list object in the heap. We'll talk about the heap in a second. And sets the reference count to 1.
Because there's one post-it note attached to it, the A.
Right. Ref count is 1. Now you write B equals A. You add a second post-it note.
The reference count instantly jumps to 2.
Makes perfect sense. Now let's say AA goes out of scope. Maybe it was inside a function and the function finished running. The name of doe disappears. The reference count drops back to 1.
And if B disappears?
The reference count hits 0. And this is where the magic happens.
Okay.
When the count hits 0, Python knows that nobody can reach this object anymore. It's floating in the void. It is unreachable code.
So the garbage collector comes along.
The janitor of memory.
The janitor sweeps it away and frees up that memory space for new data. This is immediate in CPython. As soon as that count hits 0, the memory is reclaimed.
Is it always that perfect, though? What if I have a situation where object A points to object B and object B points back to object A, but nobody else points to them?
Ah, the circular reference. That is the Achilles heel of simple reference counting.
Because if A refers to B and B refers to A, their counts are both 1. They will never hit 0.
Exactly. They would live forever, eating up your RAM, if Python didn't have a secondary mechanism called the cyclic garbage collector.
So there's a backup janitor.
Yes. It periodically scans memory, looking for these isolated islands of objects that reference each other but aren't connected to the main program, and it kills them.
That sounds like it takes extra work. It does. Relying on that adds overhead. As an ML engineer, you want to manage your references cleanly so the simple reference counter can do its job fast.
You mentioned the heap earlier.
Yeah.
And I know there's also the stack. I feel like these terms get thrown around a lot in computer science, but let's visualize them for our listeners. What is the map of Python memory?
Great question. Let's simplify it into 2 zones. Zone 1 is the stack. Zone 2 is the heap.
Stack and heap, got it.
The stack is like your orderly office desk. It's fast, it's structured, but it's small. It operates on a last-in, first-out basis. This is where the variable names live.
The post-it notes live here.
Exactly. The post-it notes live on your desk. So A, B, config, model, these names are on the stack.
Okay.
Now, zone 2, the heap, is a massive, chaotic warehouse down the street. This is where the actual things live. The heavy NumPy arrays, the pandas data frames, the neural network weights.
They are way too big for the office desk.
Precisely. So when you say df equals pd, reads csv data.csv.
The name df sits on my stack on the desk.
Right. But the actual millions of rows of data are created in the heap, in the warehouse. The df variable on your desk just holds the directions to where that data is sitting in the warehouse.
This helps explain the function passing we talked about earlier. When I pass df to a function, I'm not moving the warehouse. I'm just copying the address from my desk and handing it to the function.
Exactly. You are saying, hey, go to aisle 4, bin 12. That's where the data is.
And if the function goes to aisle 4, bin 12, and shreds the documents,
well, the documents are shredded.
they are permanently shredded for everyone.
That is a terrifyingly clear image. So we have this shared warehouse, but surely not everything can be shredded, right? This brings us to a crucial distinction: mutable versus immutable types.
This is the Team A versus Team B of Python data types. You have to know which team your data is on. If you don't, you will introduce bugs that are basically impossible to trace.
Let's start with the stubborn ones, the immutable team. The immutable team consists of things that cannot be changed once they are created. This includes integers, floating point numbers, strings, and tuples.
Wait, integers? But I can change a number. If I have a equals 10, I can write a equals 20 on the next line. I do that all the time in loops.
Ah, but look closely at what you just did. You didn't change the number 10.
I didn't?
No. The number 10 is an eternal concept. It sits in memory as an object 10. It is immutable. When you wrote A equals 20, you created a new object, the number 20, and you moved the post-it note A from the 10 object to the 20 object.
Oh, so the 10 is still sitting there until the garbage collector eats it, but I just moved my tag.
Exactly. You didn't mutate the object, you reassign the reference. This is why if you have A equals 10, B equals A, so both point to 10, and then you say B equals 20, A is still 10.
Because I moved B's tag, but A's tag stayed put.
You got it.
Okay, that feels safe. That feels predictable.
It is. That's why we love immutable types. They are thread safe, they are hashable, which means they can be keys in a dictionary and they don't have side effects, but then We have the mutable team.
The shapeshifters.
Lists, dictionaries, sets, NumPy arrays, pandas, data frames. These are objects that allow you to change their contents without creating a new object.
So if I have a list, A equals 1, 2, that lives in the heap, I stick a tag A on it, then I say B equals A. Now I have 2 tags on the same list.
Correct. Now you execute b.append3.
I am telling B to add the number 3 to the list.
You are going to the warehouse, finding the object 1, 2, and tacking a 3 onto the end of it. You modified the object in place.
You didn't create a new list. You just mutated the existing one.
And because A is still pointing to that exact same object,
When I print A, it now says 1, 2, 3.
even though you never touched A in your code.
This is action at a distance. And in a complex ML pipeline where A is your training data and B is some temporary variable inside a preprocessing function, this is how you silently corrupt your model.
Without a single warning from the compiler.
This distinction is just vital. But it gets even trickier when we talk about checking if things are equal. I remember learning about the double equal sign versus the is keyword.
Yes. This is a common interview question, but more importantly, it's a huge common bug source.
So double equals checks for equality. Do these things look the same? Do they have the same value?
Right. A double equals B calls the EQ method under the hood. It asks, is the value of A equal to the value of B? If I have 2 separate lists that both contain 1, 2, 3, double equals will return true.
Because they look the same.
Okay.
But the keyword
Yep.
is checks for identity.
Is asking a much stricter question. It asks, are these the exact same object in memory? Do they live at the same address? In C terms, do the pointers store the same memory address?
So if I have 2 separate lists, list 1 equals 1, 2, 3, and list 2 equals 1, 2, 3, they have the same value, so double equals is true.
But there are 2 different objects created in different times.
So is would be false.
Correct. They are like 2 identical twins. They look exactly the same, but they're 2 completely different people.
Now, you mentioned earlier that integers are immutable. So if I have A equals 10 and B equals 10, are they twins or are they the same person?
That is where Python gets clever. There is a mechanism called small integer caching. Python pre-allocates small integers, usually from -5 to 256 when it starts up.
It creates them once and keeps them ready.
Exactly. So if you write A equals 10 and B equals 10, Python sees you on a 10, grabs the pre-made 10, and points both A and B to it.
So A is B is actually true for small numbers.
Yes. But try this with larger numbers. If you open your terminal and type A equals 1,000, B equals 1,000, and then A is B.
It returns false.
Usually, yes. Since 1,000 is outside that cached range, Python creates a new 1,000 object for A and a different new 1,000 object for B. They are twins, not the same person.
That is wild. And I've heard this depends on how you run the code, right? Like a script versus the interactive shell.
Exactly. The compiler can sometimes optimize this within a single code block. That's why the golden rule is this. Never, ever use is to check if numbers are equal. Only use double equals for values.
So when should we use is?
You use is for singletons. The most common one is none. You should always write if value is none, because there is only one none object in the entire Python universe.
Okay, that's a really clear takeaway. Don't use is for math, use is for none.
Exactly.
Now, I want to circle back to that nightmare scenario about the experiment configurations. The one where we had a dictionary inside a dictionary and changing one experiment ruined the other.
Ah, the nested trap. This is where the distinction between shallow copy and deep copy ruins lives.
We talked about shallow copies. Can we unpack that?
Yeah.
Because I think a lot of people think config.copy makes them safe.
It's a very reasonable assumption. You have a dictionary called config. You run config2 equals config.copy. You think, great, I have a totally new dictionary.
And you do, right. You have a new container.
But what is inside that container?
References, post-it notes.
Exactly. A shallow copy creates a new outer box, but it fills that box with the same references that were in the original box. It copies the post-it notes, not the objects they point to.
So if my config has a list of layers, like layers, :6432, the new dictionary config2 has a key layers, but it points to the same list, 6432 in the heap, as the original config.
It's a shell game. You think you have a new config, but the guts are shared.
It's like giving someone a copy of your keyring. You give them a new keyring, the dictionary, but the keys on it still open your house. So if they enter the house and move the furniture, append a layer to the list, your furniture is moved too.
That's a perfect analogy, and that's exactly how experiment A gets corrupted by experiment B.
So what's the fix? How do we actually clone the object?
You need the nuclear option. Deep copy.
Deep
You'll
copy
have
file.
to import the copy module, import copy, and then use config2 equals copy.deepcopy passing in config.
What does deep copy do differently?
It's recursive. It walks down the tree. It copies the dictionary. Then it looks inside and says, oh, a list. I'll copy that too. Oh, objects inside the list. I'll copy those too.
It goes all the way down.
It goes all the way down until everything is a brand new independent object.
So it's a true clone, no shared references anywhere.
Correct.
But wait, if it's recursive and copying everything, isn't that incredibly slow? If I have a massive data structure, won't deep copy just freeze my program?
You are absolutely right to be skeptical. Deep copy is expensive. It requires serialization and deserialization of memory. It is orders of magnitude slower than a shallow copy.
So we shouldn't just use it blindly.
No. Use it for things like configurations, hyperparameters, or small state objects, things that are complex but small.
Okay.
You do not use deep copy on your 10 gigabyte training data set every time you loop. That would be suicide.
So for the big data, we rely on the shallow copy, but we treat it as read-only.
Exactly. Or we use specialized copying methods provided by libraries like NumPy or Pandas, which are optimized for speed and C.
Speaking of specialized libraries, let's shift gears to some real industry patterns. We mentioned the scalar bug in the intro. This is huge in feature engineering.
It is. Feature engineering is all about transforming raw data into something a model can understand. You usually write a class, maybe class scalar, and inside you have a method transform x.
And the logic seems simple enough. You want to subtract the mean. So you write x minus equals x dot mean.
And that line right there, x minus equals, is an augmented assignment. In Python, for mutable objects like NumPy arrays, that operator maps to in-place subtraction.
It tells Python, update x right here, right now, in the same memory address.
And x is your raw data set. By running that line, you have destroyed your raw data. You have overwritten it with the scaled version.
If you ever needed to look at the original values again, maybe to debug or to calculate a different metric you can't, they are gone.
Or like in our nightmare scenario, if you pass your validation set into this transformer.
You just scaled your validation set.
And if you run it again, maybe you have a bug in your loop, you scale it again and again.
Yeah.
Your data drifts further away from reality every time you run the cell.
This is why notebooks are dangerous. You run a cell twice, and your data is double scaled.
That is terrifying.
To fix.
Always create an explicit copy first. Inside your transform method, the first line should be xcopy equals x.copy. Then do your math on xcopy and return xcopy.
The original x alone. Treat it as sacred.
Exactly. This is functional programming 101. Avoid side effects. Your function should return your result, not modify the inputs.
There's one more classic trap I want to discuss before we get to our project.
Yeah.
The default mutable argument. This is a Python interview favorite, but I've seen senior engineers fall for it.
Oh, yes. Def train model, comma, history equals empty list.
It looks so innocent. You want the default value of history to be an empty list. So if I don't provide a history, start with a blank one.
But here's the secret. Python is an interpreted language, but function definitions are executed only once, when the module is loaded.
Wait, only once?
Once. So that list is created when you load the script, and that same list object is used every single time you call the function without an argument.
So it's a zombie list. It lives across function calls.
It is. If I call train model 1, it appends the loss to that list. If I call train model 2 later, it appends its loss to the same list. Suddenly, model 2 thinks it has model 1's history.
That is nasty.
Yeah.
So history just keeps growing and growing forever.
Until you restart the kernel. Now, I will play devil's advocate for a moment. This behavior is actually intentional in Python.
Intentional. Why would anyone want a zombie list?
It allows for caching. If you want a persistent object that remembers state between calls like a memoization cache, you can use a mutable default argument. It's a hack, but it works.
Okay, fair enough. But for 99% of us who just want an empty list, how do we kill the zombie?
You use none. The signature should be def train model, comma, history equals none.
Then what?
Then inside the function you write, if history is none, history equals empty list.
Ah, because the code inside the function runs every time.
Exactly. That guarantees you get a fresh, new, empty list for every call.
Such a simple fix. But if you don't know it, you could spend days debugging why your models are sharing loss curves.
Absolutely.
Okay, we have covered the theory, the nightmares, and the fixes. Now, let's apply this. We are starting our first mini project today. OS Automator.
Yes, we are building a clean, professional file organizer. The goal is to scan a directory and organize files by type or date. It's a great way to practice safe memory handling.
And today, we are focusing on the source organizer.py file. We need to implement a function called organize files.
Right. Now, files is likely a list of file names passed from some other part of our program. To organize them, we probably need to sort them first.
Natural instinct, files.sort.
Stop right there. Files.sort is an in-place list method.
So if I pass my master list of files into this function,
You have just rearranged the master list for the entire program. Maybe another part of the program relied on the original order. Perhaps they were sorted by date, and you just resorted them by name. You just broke the other module.
so applying our memory discipline.
We have two options. Option A, write files equals files.copy first, then files.sort. We work on our local copy.
And option B?
Option B, use the built-in sorted function. New files equals sorted files. Sorted always returns a new list and leaves the original alone.
I like option B. It's cleaner.
It is. It's more Pythonic.
And we are not just writing this code, we are committing it. The commit message should be add memory-safe file organization logic.
I love that. Memory safe. It sounds professional because it is professional. Engineering is about safety and discipline, not just making it work on your machine one time.
And this project is going to grow, right? This is week 1.
Yes. Next week we add testing, type hints, config separation. We are building a system, not a throwaway script.
Fantastic. So before we wrap up, let's give our listeners a mental checklist. When they are about to push code, what should they ask themselves?
I have a 5-point memory discipline checklist. Number 1, are mutable objects like lists, dicts, data frames copied before I modify them? Number 2, if I have a nested config, am I using deep copy?
Check.
Number 3, am I checking identity with is only for whyatus? None, not for values.
Right, it's double equals for values.
Number 4, if I'm debugging, does IDTrain data differ from iTest data? Check the addresses.
See if they point to the same warehouse bin.
Exactly. And number 5, are my transformers returning new objects or mutating old ones?
That's a solid list. Print that out, stick it on your monitor.
It will save you from the nightmares we started this deep dive with.
So to summarize the journey today, we learned that variables are references, not boxes. We visualized the stack desk and the massive heap warehouse. We met the immutable and mutable teams.
We learned why double equals is not is. We saw the danger of shallow copies in nested structures. And we learned how to kill the zombie default argument.
And we learned that memory discipline is the bedrock of reliable ML engineering. If you don't understand where your data lives, you can't trust your results.
Correct.
Now, it is time for the practical task. We don't just want you to listen, we want you to code.
Yes. Go to your repository ML Engineering Foundation source directory and create a file named memorydiscipline.py.
Memorydiscipline.py. I like the sound of that.
In that file, I want you to prove everything we just said. First, prove immutable versus mutable behavior. Change a list and see the original change. Change an integer and see the original stay the same.
Prove it to yourself.
Second, demonstrate the nested shallow versus deep copy trap. Create a dictionary with a list inside. Copy it, modify the copy, and watch the original break. Then fix it with deep copy.
Nice.
Third, simulate the transformer mutation. Write a dummy class that modifies data in place. And crucially, use the id function, printed variable. This prints the memory address. Prove to yourself that two variables have the same address.
Don't just take our word for it. See the numbers match in your console. If the IDs match, it's the same object.
Exactly. When you see those matching ID numbers, the concept really clicks.
And when you are done, commit it with the message. Implement memory model experiments and push it to GitHub. Build that portfolio.
It's a great exercise.
So what is coming up next? We understand references now.
Well, now that we know how references work, the next logical question is, how do these mutable data structures silently corrupt feature engineering pipelines in more complex ways? We touched on it today, but next time we are going deep into mutability, copying strategies, and silent data corruption in real ML systems.
We are going to break some pipelines.
And then we're going to fix them.
I can't wait. If you found this deep dive helpful, try the exercise. Write your questions in the comments below. We love seeing those 80 outputs, and don't forget to like, share, and subscribe to 60 Seconds Academy.
Happy coding, and stay memory safe.
See you in the next deep dive.